Quality planning. Voice of the customer, VOC. How often have you encountered products, services, or processes that fall short of meeting your expectations as a customer? Or perhaps you've dealt with upgraded websites or apps that have become more cumbersome, requiring extra steps or clicks to complete a simple task. Remember, quality is about meeting the customer's needs. It's about ensuring that what you offer is truly fit for use. This is why it's crucial that, during quality planning, customers are accurately identified, and their needs are thoroughly understood, allowing the development of features and functions that align with their expectations. This is where the voice of the customer, VOC, comes into play. VOC refers to the needs and expectations articulated in the customer's own words. These are then translated into critical to quality, CTQ, requirements. So, how do you gather VOC? Start by identifying and listing your customers, anyone who benefits from your product, service, or process, whether they are internal or external to your organization. Customers should be grouped into segments based on their unique needs, such as sales, industry, location, demographics, or usage. For instance, the requirements of commercial and residential customers will differ if you sell power generators, just as government and enterprise clients will have distinct needs if you provide software solutions. VOC encompasses two types: the customer's expressed needs before experiencing the product or service, and the feedback after they have used it. The former is essential for determining the right features and functions, forming the foundation of quality planning. The latter provides valuable insights for performance feedback, enabling corrective actions or even sparking quality improvement initiatives for chronic issues. Feedback also informs lessons learned, feeding back into the quality planning process. VOC can be collected through various methods such as surveys, focus groups, interviews, and observations. For a deeper dive into these methods, check out my video titled Collecting VOC in the Six Sigma Green Belt course. Once VOC is collected, it's crucial to translate it into terms your design team can understand, specifically, CTQs. CTQs are the key performance characteristics that are vital to customers, guiding the design team in developing features that truly matter. Because CTQs are measurable, they help set the right specifications and targets that will meet or even exceed customer expectations. To learn more about CTQs, you can watch the CTQ video in my Six Sigma Foundations course. Remember, designing features without a clear understanding of what's critical to your customers is a recipe for failure. Quality, after all, is about delivering the right features without defects. The Kano model: when customers are in the market for a new product or service, what factors do you think influence their decisions? What qualities are crucial to not only attracting new customers but also satisfying existing ones to the point where they become enthusiastic promoters of your brand? The answer lies in understanding the Kano model, a framework developed by Dr. Noriaki Kano, which helps you grasp how customers perceive quality. This model categorizes attributes into three types that affect customer satisfaction and dissatisfaction: basic quality attributes, dissatisfiers; performance quality attributes, satisfiers; and excitement quality attributes, delighters. Imagine the Kano model as a graph. The vertical axis represents customer satisfaction, ranging from extreme dissatisfaction at the bottom to high satisfaction at the top. The horizontal axis represents the degree of execution, from poor performance on the left to exceptional performance on the right. Let's break down these categories. First, there are dissatisfiers, or basic quality attributes. These are the non-negotiables that must be present for a product or service to function adequately. Their absence leads to dissatisfaction, but their presence won't necessarily increase satisfaction. Take an electric vehicle, EV, as an example. Customers expect the car to operate safely without incidents like fires or explosions. While meeting this expectation won't generate excitement, failing to meet it will certainly cause dissatisfaction. Next, we have satisfiers, or performance quality attributes. These are features where the level of execution directly influences customer satisfaction. For example, with EVs, the longer the range on a single charge, the more satisfied the customer will be. Conversely, a shorter range would decrease satisfaction. Finally, there are delighters, or excitement quality attributes. These are the unexpected features that can wow customers and elevate their satisfaction to new heights. Their absence won't cause dissatisfaction, but their presence can create delight. For instance, imagine if your EV could double as a generator for your home. This kind of feature could lead to excitement and significantly boost customer satisfaction. Understanding the Kano model is crucial in quality planning and product design. Ensuring that basic quality attributes are met is essential to prevent dissatisfaction. Performance quality attributes should be optimized to enhance customer satisfaction, and incorporating excitement quality attributes can help differentiate your product or service in the market. So, the next time you consider an EV or any other product, think about how these attributes shape your overall experience, from avoiding dissatisfaction to achieving satisfaction and even delight. Quality function deployment, QFD. Too often, new product development follows a fragmented process, where each department handles its piece in isolation, leading to what I call the tossing over the wall syndrome. Design teams create their plans and then hand them off to engineering, who generate specifications before passing the baton to manufacturing. This disjointed approach often leads to miscommunication, resulting in a disconnect from the customer's voice. However, there is a solution that promotes seamless collaboration across all departments. Quality function deployment, QFD. Developed in 1972 at Mitsubishi's Kobe shipyard in Japan and later adopted by Toyota with remarkable success, QFD has proven to significantly reduce product development time, enhance quality, and lower the cost of launching new products. It is now a widely adopted tool in various industries worldwide, from automotive to services. QFD is a structured approach that translates customer needs into product and process specifications through a series of interrelated matrices, known as the House of Quality. These matrices map out the relationships between customer requirements and technical specifications, ensuring that every department is aligned and focused on fulfilling customer expectations. In this overview, we'll explore how QFD works, breaking down the components of the House of Quality, from documenting customer requirements to setting technical targets and evaluating competitive analysis. By the end, you'll see how QFD transforms product development into a cohesive process where every team is aligned, and the customer's voice remains central throughout. In the following video, we'll delve deeper into how QFD ensures that all teams are in harmony, effectively eliminating the tossing over the wall issue and keeping everyone on the same page. QFD customer requirements flow down. In quality function deployment, QFD deployment refers to the systematic breakdown of customer requirements into critical to quality (CTQ) elements, which are then used to identify the key features and processes necessary to meet those requirements. This is accomplished through a series of planning matrices, often referred to as the houses of quality. In our previous video, we explored the basics of QFD and took an in-depth look at the first house of quality. Now, we'll delve into how customer requirements are cascaded through the subsequent houses in QFD. Initially, customer requirements are converted into technical specifications or CTQs within the first house. By mapping and analyzing these relationships, a prioritized list of technical requirements and their corresponding targets is established. Moving to the second house, these technical requirements are used to define the product features and components necessary to support the CTQs. The interrelationships are again mapped and prioritized, highlighting key features and their objectives. In the third house, these identified product features guide the development of the processes needed to achieve them, leading to a prioritized list of process goals. Finally, the fourth house focuses on determining the process and quality controls essential to achieving the identified process goals. Together, these four houses of quality ensure that the voice of the customer is systematically translated from initial requirements to specific products, processes, and controls in QFD. Design for Six Sigma. Achieving quality through intentional design is always preferable to relying on detection and inspection after the fact. The goal is to create a product or service that not only meets but exceeds customer expectations, with the right features and free from defects. This is the essence of Design for Six Sigma, DFSS. DFSS is a structured methodology aimed at designing or redesigning products, processes, and services to ensure they meet critical customer needs and requirements. One of the key principles of DFSS is that quality is integrated into the design from the outset, rather than being inspected at the end. This approach focuses on understanding and incorporating customer expectations and requirements right from the start. Another crucial aspect of DFSS is the concept of requirements flow down and capability flow up. Information flows between the customer, functional, product, and process domains to ensure that customer needs are translated into specific design and process requirements. Requirements flow down involves cascading customer needs through various domains to ensure that each level of design and production aligns with these needs. In contrast, capability flow up is about feeding back information on the capabilities of the design and processes to ensure they meet the defined requirements. This iterative process helps to refine and validate the design, ensuring that the final product is capable of meeting the critical to quality (CTQ) performance targets. The DFSS methodology involves translating customer needs into measurable CTQs, which then guide the development of functional requirements, conceptual designs, and detailed product features. These features are then refined into specifications, and process parameters are optimized to ensure quality. The final design is thoroughly tested to confirm it is both producible and meets customer needs. DFSS is typically carried out through a phased approach known as DMADV: define, measure, analyze, design, and verify. There are variations of this approach, such as DMADOV, where O stands for optimize, and IDOV, identify, design, optimize, verify, but the fundamental flow of requirements and capabilities remains consistent. This structured approach ensures a systematic way to address customer needs, leading to a design that is predictably capable of delivering quality outcomes. If you're involved in designing or redesigning a product, process, or service, DFSS provides a reliable framework to achieve these goals. Design FMEA. Addressing quality issues early in product development is not just more efficient, but also significantly more cost-effective. The cost to rectify a quality problem during development might be X dollars, but that cost can skyrocket to 10x during production and reach as much as 100x when the product is already in the hands of customers. Clearly, it's worth the effort to identify and fix these problems as early as possible. One effective method for doing this is through design failure modes and effects analysis, Design FMEA. This tool helps you anticipate and mitigate potential failure points in your design, product, or service. However, Design FMEA isn't something to be done in isolation. It's best carried out collaboratively with key stakeholders and subject matter experts. If you're interested in learning more about how to effectively plan and execute a Design FMEA session, there's a comprehensive video available on LinkedIn Learning. To get started, let's look at a Design FMEA template. The first column lists the design function, system, subsystem, or component. Let's use a coffee maker as an example to walk through the process. First, ask, for each design element, what could possibly go wrong? These are potential failure modes, listed in the second column. For instance, one component might be the lid door. What could go wrong here? The potential failure modes could include the lid not sealing tightly. Next, consider the consequences of these failure modes. How severe are these potential effects, rated on a scale from 1 to 10, where 10 is the most severe? For example, if the lid doesn't seal properly, this could pose a significant safety risk, earning a high severity score. Then, consider the potential causes of each failure mode. How likely are these causes to occur, again rated on a 1 to 10 scale? This is the occurrence score. For example, causes might include poor assembly or hinge design. The next step involves evaluating your current design controls to detect these failures. How likely is it that these controls will catch the problem? This is the detection score, where 10 indicates that detection is unlikely. When you multiply the severity, occurrence, and detection scores, you get a risk priority number, RPN. The RPN helps prioritize which failure modes to address first. In our coffee maker example, the highest RPN might be associated with the lid not sealing or water spewing during brewing, both of which require immediate attention. On the right side of the DFMEA, you'll find recommendations for mitigating these risks. Once actions are taken, the RPN should ideally decrease, indicating reduced risk. This is how a design FMEA helps ensure your design is robust and minimizes the risk of failures. While it's easy to hope that nothing will go wrong, proactively identifying and mitigating potential risks through a design FMEA is a wise approach to safeguard your product's quality. Reliability and quality. Your neighbor might proudly share that they chose their new car because it comes with a 5-year, 60,000-mile bumper-to-bumper limited warranty. But what does this really mean? It signifies that the manufacturer is confident the car will perform reliably within that timeframe or mileage limit. Let's focus on the term reliable or reliability. Reliability refers to the consistency with which a product, system, or service performs as expected over time. It's about how long it will continue to function without failure. While quality measures how well something performs, reliability adds a time-based perspective, essentially asking how well the quality holds up as time progresses. To illustrate, NASA defines reliability as the probability that an item will perform its intended function without failure for a specified period under defined conditions. On Earth, we also desire reliability in our products, equipment, and services. The American Society for Quality, ASQ, defines reliability as the likelihood that a product, system, or service will adequately perform its intended function for a specified period, or operate in a defined environment without failure. Quantitatively, if we denote time to failure by T, reliability is the probability that an item will not fail before a given time T, assuming it starts functioning properly at time 0. However, reliability typically decreases over time, as no item can last forever without failing. It's often measured by the failure rate, or the number of failures per unit of time, during the period of interest. For repairable items, reliability is gauged by the mean time between failures, MTBF. To enhance reliability, consider these strategies. Reduce system complexity during design by eliminating unnecessary components. Improve the reliability of individual components. Incorporate redundancy so that if one component fails, others can take over, and design for easy maintenance, allowing for preventive component replacement. Ultimately, design plays a critical role in determining reliability. Remember this in your next project, because reliability is all about how well your quality endures over time. Availability and maintainability. Power outages are something we've all experienced, and they highlight our reliance on having electricity available whenever we need it. But what exactly does availability mean? Availability refers to the capability of a product, system, or service to perform its intended function under specific conditions, when required. It is quantified as the ratio of operating time to the total time, which includes both operating time and downtime. For instance, if your phone is functional for 16 hours but loses signal for an hour, its availability is 15 out of 16 hours. This type of availability is known as operational availability, which considers total downtime. On the other hand, intrinsic availability focuses solely on active repair time. If the repair time for your phone's signal loss is 15 minutes, the intrinsic availability would be 15 hours divided by 15.25 hours. In real-world applications, these calculations use mean values. Operational availability is calculated as the mean time between failures, MTBF, divided by the sum of MTBF and mean downtime. Intrinsic availability uses MTBF divided by the sum of MTBF and mean time to repair, MTTR. High availability indicates that a product or system is reliable and repairs or replacements are done swiftly. To maintain high availability, regular maintenance is crucial, whether it's a car, system, or equipment. This leads us to maintainability, which addresses how easily a system can be maintained. While a maintenance-free system would be ideal, it's not always possible. Preventive maintenance can reduce the frequency of failures, while corrective maintenance restores functionality when breakdowns occur. Maintainability is typically measured by MTTR. The design of a product significantly impacts its maintainability. Modular designs, for instance, allow for quick diagnosis and replacement of faulty components. Additionally, built-in diagnostic features, like those in modern vehicles that alert you to low battery or tire pressure, enhance maintainability. Ultimately, availability and maintainability are critical factors in determining the quality and usability of a product or system. A well-designed system not only minimizes downtime but also ensures that any necessary maintenance is straightforward and efficient. By prioritizing these factors in design, you can create products that are reliable, easy to maintain, and consistently available for use. Designed for manufacturability, a well-designed product is one that can be manufactured efficiently with minimal risk of defects. The decisions made during the design and development phases significantly influence manufacturing ease, speed, specification compliance, and overall product cost. In essence, the goal is to design for manufacturability, DFM. This approach emphasizes streamlining a design to enhance its producibility, integrating product design and process planning from the outset. Often referred to as DFMA, Design for Manufacturing and Assembly, this method combines the principles of DFM and DFA, Design for Assembly. DFM focuses on selecting cost-effective raw materials and components, reducing manufacturing complexity, and improving the ability to meet quality standards while keeping costs low. DFA, on the other hand, aims to simplify the assembly process, minimize the potential for assembly errors, and reduce assembly time and costs. DFMA originated from the pioneering work of Boothroyd and Dewhurst in the 1960s and is now widely adopted in the manufacturing industry to shorten development cycles, lower costs, boost productivity, and enhance product quality. Key guidelines for DFMA include minimizing the total number of parts used, which reduces manufacturing costs and the likelihood of errors. Standardizing parts and reducing the variety of components further streamline purchasing, inventory, and production processes, while reducing lead times and costs. Simplifying manufacturing operations and assembly steps not only speeds up production but also improves quality by decreasing the chances for mistakes. Ensuring process capabilities can consistently meet specifications is crucial, as is setting realistic specifications and tolerances to avoid unnecessary precision that doesn't contribute to the product's fitness for use. Using standard components wherever possible, even in high-end products, can significantly reduce costs without compromising quality. Modular design further simplifies manufacturing, maintenance, and service. Additionally, designing for part commonality and symmetry can make assembly more intuitive and reduce orientation errors. Minimizing tooling requirements also helps cut down on costs and production time. While these are core principles, DFMA is a comprehensive field with extensive literature available for those seeking deeper knowledge. Ultimately, the critical takeaway is that manufacturing and assembly considerations should be integral to the design process from the very beginning.